Okay, let's go ahead and wrap up the t-test lecture video. So when we violate our basic assumptions, right, when the conditions that need to be met for these tests to work as they're designed to work, when those are violated, a lot of people ask me, should I just throw out my data? Do I have to recollect data all over again? And you know what? I really feel bad for people because people put a lot of time and effort into collecting data for these research studies. They had the perfect intention of using the right statistical procedure, and they violated the basic assumptions for the statistical procedure. So I often get this as an issue, and there are some remedies that we can move forward with. So when we talk about violations to the basic assumptions, we have what are known as non-parametric equivalents or non-parametric friends to the parametric statistics. So in the case of an independent samples t-test, if we violated any one of those basic assumptions, the non-parametric equivalent would be to use a Mann-Whitney U-test. Okay. And effectively, the Mann-Whitney U-test serves the same functions as the independent samples t-test, but instead of using means and standard deviations, we're using something that is known as ranking, mean ranks of the data in order to determine those differences. So it's not the same thing as doing arithmetic and saying, is the difference between this mean and standard deviation different from this mean? We're looking at ranks and determining if the prevalence of how often a particular value is showing up, if that is showing up more than what should be expected, and if that happens more so in one group compared to the other, you can make an inference that something's going on with the independent variable. You're just not able to determine it definitively with mean arithmetic math. In the dependent samples t-test, right, or the paired sample or matched samples t-test, the non-parametric friend is something that's known as the Wilcoxon sign rank test. And once again, we're using mean ranks here, but instead of using means, we're using mean ranks of data and determining if the prevalence of something that is more highly ranked, if that is statistically happening more than what it should be compared to sampling error alone. And so we do have some remedies in terms of how we can use these parametric and non-parametric procedures, and these are the procedures that we'll get into. So from the perspective of parametric versus non-parametric statistics, it's important to understand that with parametric statistics, typically we assume the normal distribution of the dependent variable is true, right? So when we collect data on a dependent variable of interest, we assume that the data is going to be at least interval or ratio level of measurement, and we assume that there's going to be a normal distribution of the histogram for that dependent variable with a sample size at or about 30 participants. But in a non-parametric statistic, we don't have as strict criteria for those basic assumptions. So if you violate the normal distribution assumption, that's not a deal breaker in a non-parametric procedure like it would be in a parametric t-test. You don't necessarily need a large sample size. So like in a parametric test, you may need 30 or more participants. You don't need to worry about sample size as much in a non-parametric procedure. And then lastly, non-parametric tests also allow for the dependent variable to be categorical in nature, specifically ordinal or interval level of data. And so non-parametrics are really sort of a get-out-of-jail-free card for the parametric procedures when your data runs into issues like this. So one of the things that we talked about is that with the violation of the basic assumptions for a independent groups or an independent samples t-test is that the Mann-Whitney U-test is the non-parametric friend to that test. So if we violate basic assumptions, this is the test that we're going to want to be able to perform. And so the key to a Mann-Whitney U-test is that the dependent variable of interest that's collected needs to be either ordinal level of measurement. So if it's categorical, it needs to be able to be organized in some logical or meaningful fashion, or it needs to be continuous, okay? But it does not require the normal distribution assumption to be met in order to use this test. So if you violate a basic assumption of normality and you have a test that really fits an independent samples t-test design, use the Mann-Whitney U-test and you'll be able to determine it just fine. So what are some of the basic assumptions of the Mann-Whitney U? We assume that the dependent variable is at least ordinal or ratio or interval level of measurement. We assume that the independent variable or categorical variable is still nominal or ordinal, right? And we assume that we have independent observations. So the people in one group are not the same people as those in the other group. That's consistent with the independent samples t-test. And we do not assume a normal distribution. So if those criteria are met, you can go ahead and use the Mann-Whitney U-test. So when you run the statistics for a Mann-Whitney U-test, you'll notice here that you have, and this is just hypothetical data, you'd have values for the group of people, so 40 participants, the mean rank, the standard deviation, the smallest number, the largest number, and their percentiles. Those at the 25th percentile, those at the 50th or the median, and those at the 75th. So when you run the inferential statistic, you can see that you're given data for what's known as ranks and test statistics. So just how you did the math to determine the t and then compared the t to the t critical value and made your decision based off of that, we're going to look at the Mann-Whitney U-test here, and you can see that in the case of a study design where cholesterol is the dependent variable being measured, you can see that there's a diet group and there's an exercise group, 20 in each group, and the mean rank of cholesterol for people that had the diet group was 25, and the mean cholesterol concentration in the exercise group was 16. And so when you run your test statistic and perform the math, you can see you have a value of a Mann-Whitney U of 110, and your z-score is negative 2.446. There is a z-distribution. So remember, the z-distribution in a 95% confidence interval is plus or minus 1.96. So if the absolute value on a two-tailed test is larger than 1.96 in either tail, it's statistically significant. And that would tell us that the mean rank of the cholesterol concentration in this example is different between those who had the diet intervention and who had the exercise intervention. And similarly, when we look at the p-value, right, we would expect that the p-value being smaller than 0.05 means the probability of making a type 1 error is smaller than 5%. Any number, when you see p, or in this particular case, sig, the sig in this case represents the p, if that number is smaller than 0.05, then you have a statistically significant finding, which means the observed z-score in this case for the Mann-Whitney U is statistically different from the critical value. And so when that number is smaller than 0.05, as it is in this case, 0.014, it means there's a statistically significant mean rank difference between diet and exercise groups with respect to cholesterol concentration. Okay, so now that we know a little bit about how we can bail ourselves out from a violation to a basic assumption in an independent samples t-test, let's look at this now for the paired sample t-test. So the Wilcoxon sign rank test, as we said, is the non-parametric friend to the paired sample t-test. The dependent variable in this case, similar to the Mann-Whitney U-test in the independent samples case, must be at least ordinal, ratio, or interval level of measurement. And the basic assumptions or conditions that need to be met for this non-parametric test to work is that the dependent variable has those levels of measurement. The independent categorical variable is nominal or ordinal. And we have two related groups, because remember, that's a similar thing. In a paired sample t-test, we had to have related groups. And so in a Wilcoxon sign rank test, we have to have related groups as well. But we do not expect a non-normal distribution. We do not expect a normal distribution in this case, which we do assume in a parametric paired sample t-test case. Okay, so if we look again at the descriptives, let's say we assessed patients' pain scores before and after a treatment. And so the same group of people, 25 people N and 25 people post, mean pain scores, mean rank pain scores, standard deviations, the smallest observed case, the largest, the 25th, the 50th, and the 75th percentile. You have your descriptive information. You can summarize the sample in one case. If you look again at those that have negative ranks versus positive ranks, right? We're doing this mean ranking procedure, and our z-test in this particular case is minus 1.807. So remember, z-distribution, the 95% of the scores are going to fall within two standard deviations above and below the mean. The actual number, as I said before, 1.96. And so if the absolute value of the z-score here is larger than 1.96, it means there's a statistically significant difference in the pain scores pre to post treatment. In this case, you can see that the observed difference in the z-score is negative 1.807, which does not exceed the critical value of plus or minus 1.96, and that is supported by a p-value or a significance threshold that's larger than 0.05. Okay, so I hope this was helpful. There'll be a couple other videos that we'll get into in a few minutes about how to perform this in SPSS and JASP, and we'll do some live demonstrations for those of you that come and have the hybrid version in a face-to-face class setting.